Number 4. So we got stuff happening in some containers. 27 Celsius, 5 identical rigid 2-liter vessels are filled with nitrogen and sealed. I feel like we've answered this, but I don't know. 4 of the 5 vessels also contain 0.05 mole sample of sodium bicarbonate, sodium bromide, copper, and iodine, as shown in the diagram above. The volume taken up by the solids is negligible, and the initial pressure of nitrogen in each vessel is 720 millimeters of mercury. All 4 vessels needed 127 and allowed to reach constant pressure. At 127 degrees, the entire sample of iodine is observed to vaporize. How does the mass of vessel 5 at 127 compared to its mass at 27? Mass would be identical. The mass would be identical. Changing temperature doesn't change the mass. So the iodine is going to probably sublime. It says it turns into a gas, right? Vaporize, yeah. So it sublimes. It goes directly from solid to a gas. But that doesn't have anything to do with how much it weighs, or not how much it weighs, but its mass. All right. So B, the mass is the same since the number of each type of atom in the vessel is constant. It just changed state. We didn't do away with it. So we don't change mass unless we do something in nuclear physics. We won't see that in here. Everybody good with that? All right. So reaction 2 occurs when an excess of 6 molar HCl solution is added to 100 mils of sodium hypochlorite. That L in NaOCl, that L is supposed to be lowercase. That's a typo. Of unknown concentration. If the reaction goes to completion and a 0.01 mole of chlorine gas is produced, what was the molarity of the sodium hypochlorite solution? So we're looking at reaction number 2. If you produce 0.01 moles of chlorine, then we must have had 0.01 moles of sodium hypochlorite because they're 1-to-1. Everybody agree with that statement? So these are 1-to-1. Okay. So produce 0.01 moles, and that's the reactant 0.01 moles. And if it was 100 mils of solution, the concentration of sodium hypochlorite is 0.01. Which is 0.01. All right, everybody agree with that? A little stoichiometry and molar solutions. The reaction represented above goes essentially to completion. Reaction takes place in the rigid insulated vessel that initially is 600 Kelvin. All right, a sample of methanol is placed in the previously evacuated vessel with a pressure of P1, 600 K. Here's the final pressure in the vessel after the reaction is complete. And the contents of the vessel are returned to 600 Kelvin. Well, it should triple. Why? Temperature doesn't change. That's what. to a 600. So, but and whether they're proportional or inversely proportional doesn't matter. Subscripts. Triples. No, triples. Yeah, there's 3 moles of gas on the right and 1 mole on the left, right? So every mole of methanol that decomposes makes 3 moles of gas, 1 mole of CO and 2 hydrogen. So this is a 1 to 3 reaction, right? So you're going to triple the amount of stuff, you're going to triple the pressure. Right. D, triple. We're going to triple times 3. D is in dog. Multiplying by 3. Everybody understand why? It's 1 to 3.
Explain the action.
It's 1 to 3. I don't know how to explain. I mean, it's 1 to 3. There's 1 methanol and there's 1 CO and 2 hydrogens. 1 plus 2 is 3, right? Got it? So it's 1 to 3. Every molecule of methanol that breaks down, you get 1 carbon monoxide and 2 hydrogens. So one thing will make 3 things, right? 1 particle to 3 particles. Triple the amount of particles in the sealed container at same volume and temperature, and you're going to have triple the amount of pressure. Okay, so when it says rigid vessel, that means that the volume is constant. Okay. Number 7. If equal masses of the following compounds undergo complete combustion, which will yield the greatest mass of CO2? So you have equal masses. It said equal masses. So Yep. All right, so
I just want to know what's on Thursday's quiz.
didn't I just read that off a few minutes ago?
Yeah, but I'll get it from somebody else.
All right, so mass is conserved, right? Right? Okay. So the mass of carbon dioxide produced in the combustion of any of these 4 things is going to be the same as the mass, or relative to the mass of carbon that was originally in the things that are being burned, correct? Okay, so when you burn a hydrocarbon, the carbon in the CO2 comes directly from the carbon in the hydrocarbon, right? We used that thought process to do empirical formula stuff sometime back. Okay? So if you've got equal masses of those 4 things, the one that has the highest percent composition of carbon is going to produce the most carbon. Okay? So which one would that be? Which one of those you're going to get the most carbon out of? It's definitely not D, right? So there's only 1 carbon atom in each one of those. So it's got to be one of the first 3. They're all C6, right? So which one of those would be the highest percentage of carbon? Be A, right? It's got the smallest amount of anything else. 6 hydrogens is less than 12 hydrogens, which is definitely less than 12 hydrogens and 6 oxygen. Okay. That's an interesting question. All right, number 8. Got some pictures. Here we go. A group of students was asked to recover copper from a blue-green aqueous solution containing an unknown concentration of copper 2+ ions. The students took a 100 ml sample of the solution and added an excess of 1 molar sodium phosphate, causing the copper 2+ to precipitate as copper phosphate, as shown in step 1 below. Okay, so there's a balanced equation and a picture of what they're doing. Okay, so we should be able to write that balanced equation. That would be a double displacement. Okay, all right, well, they don't tell you what the other ion is, so it's really, just think of this precipitation. But the copper and the phosphate was, so copper 2+ in the blue-green solution is mixed with some other anion that is fully soluble here, probably nitrogen. Okay, and by telling you because it don't matter. The sodium in the sodium phosphate is also a spectator, correct? The first column metal is going to always spectate. It's like nitro, it's going to always spectate. Okay, until we get to electrolysis and things like that. These simple reactions are going to spectate. So we're going to make a precipitated copper phosphate. And we ought to be able to write that equation. They were kind enough to give it to us here, okay, and then pictorially show you that we've got a blue-green solution, a colorless solution. You mix them together, you're going to get a bluish-green solid settled at the bottom of it. Okay, that's pretty easy to visualize that. If we go down to step number 2, we're going to take this beaker right here and do something else to it. We're going to add hydrochloric acid to it. And that's going to do another double displacement reaction. And we're going to end up with copper chloride and phosphoric acid. So we're going to go back to a blue-green solution of aqueous copper chloride and phosphoric acid. Then we're going to do step number 3. I don't know if we're just doing this for fun or what exactly we're trying to do. But anyway, we're going to add a strip of zinc to the solution to recover the copper. Okay, we're trying to get the copper out. That's fine. You could have just done that from the start. But anyway, they're just making up a random question here. So it says you're going to add a strip of zinc that's silver colored. That's confusing, but it's zinc. Anyway, I would have just said metallic colored. I don't think I would have called it another element. Anyway, when you add that, then you're going to get a single displacement, and you're going to get a bunch of brown copper on the bottom of it. We would try to do a very similar reaction to this in a few days. We can take a day somewhere around here to try to do some demonstrations. Do a very similar one to this. All right, so then you got solid copper at the bottom. So now you got a single displacement, metal displacing metal, and then there's zinc chloride and solid copper, and the copper sits at the bottom, and you can filter it, dry it, and weigh it. Okay. If 4.6 grams of copper phosphate was recovered from step 1, what was the approximate copper ion concentration in the original solution? Which means step 2 and 3 are completely irrelevant to the question. All right. So the molar mass of copper phosphate is 381 grams per mole. So how many moles of copper phosphate did we collect? So 4.6 divided by 881. How much?
0.0121.
Good. Right. Scroll back up and see the balanced equation of step number 1. Is it 1 to 1? No, it's 1 to 3. Okay, so we got 3 times as much copper. It's a 1 to 3 ratio. So the copper would have been 0.3630. 0.3630 moles. And what What's the volume of the copper solution? Start there. Set it at the top. Let's scroll up, look. Scroll up, say what the volume of the copper solution was. 100 milliliters?
It's a sample of the solution.
All right, sounds like a good number. 100 milliliters. All right, so 1,363 molar. That's one of the choices. How about that? C. Okay, so these two, this reaction is 3 to 1, correct? So we calculated how many moles of this solid we made, which means we had to have 3 times as many moles of copper ions to begin with, right? That's the stoichiometry part of it. So we multiplied by 3, and then we divided by wherever it said 100 mils at, up here. Students took a 100 mil sample. Yep, there we go. And that gave us a concentration of 0.36 C. Rest of that was not needed. Number 9. We need to know that balanced equation right there. The decomposition of hydrogen peroxide, you need to know how that works. We probably mentioned that already. I don't remember. But we need to know how that works. All right, the decomposition of peroxide is represented by the equation above. A student monitors the decomposition of a liter sample of peroxide at a constant temperature of 300 Kelvin and recorded the concentration of peroxide as a function of time. The results are given in the table below. So what happens to the concentration of it over time? It decreased, right? It went down. It's being decomposed. That makes sense, right? Okay. All right, let's see what else they're saying here. The O2 produced from the decomposition of the 1 liter sample of peroxide is collected in a previously evacuated 10-liter flask at 300 Kelvin. Okay, so they're collecting the oxygen in a fairly large flask. What is the approximate pressure in the flask after 400 seconds? For estimation purposes, assume that 1 mole of gas in 1 liter exerts a pressure of 24 atm to 300 K. Okay, so at 400 seconds, the concentration of peroxide has dropped by 1, right? So it's 1 liter sample, so that means it's lost 1 mole, which means we've produced a half a mole of oxygen. And if 1 mole in 1 liter exerts, well, I don't know why they're telling us that. All right. So we've produced a half a mole in 10 liters, 12, 1.2, doing this in my head, 1.2, let me look, yep, 1.2, all right, here we go. All right, that's roundabout confusing. All right, here we go. So we lost 1 molar concentration, correct? You agree with that? 2.7, 1.7. So that means we reacted 1 mole because it was a 1 liter container of peroxide, right? So that means 1 mole of peroxide reacted. Which, according to the balanced equation, that means a half mole of oxygen produced. Okay? Then they give you this estimation thing here. If 1 mole of gas in 1 liter exerts 24 atmospheres at 300 Kelvin, then how much would a half a mole in 1 liter exert? If 1 mole makes 24 atmospheres, what would a half a mole make? 12, right? Okay, so 12, right? took that instead of being 1 liter, it's 10 liters. So you increase the size of the container by 10 times. What would that do to the pressure? That multiply it by 10, divide it by 10. Divide it by 10. Okay. Volume and pressure inversely proportional, right? Moore's law. So it would get 10 times lower, which means it's 1.2. Okay. See how they like to answer short geometry questions? It's a bunch of ratios and mental math, really. Yeah, so let's remember, this is a good time to point something out. The whole purpose of an AP exam, let's talk about that for just a second, because this might help you realize what you get yourself into here when you read these questions. The number one purpose of this AP exam is not to see how much chemistry you know. Okay, that's the secondary purpose, right? The purpose of this AP exam is the same as all AP exams, and it's to see how well you can think in a hurry. That's the whole purpose of all of it. Okay, is to just see how much thought you can put in, and how much you can figure out and calculate and do, think about in a very short amount of time. Because every piece of research that's ever been done says that that's what makes a successful college student. Somebody that can learn stuff in a hurry and figure stuff out on their own in a hurry. That's the way it goes. So that's what these tests are looking for, right? It's looking for people that colleges think are worthy of skipping college classes, correct? To measure your college readiness by seeing if you can think quickly on your feet and do some logical problem solving in a short amount of time. This particular AP exam, all of that is relevant to the subject of chemistry, right? But they give a test like that that's relevant to the subjects of calculus and physics and English and history and foreign languages and so on. Now, you do. The difference in AP and the ACT is you do have to know the material, but it's still measuring. The ACT measures nothing but your ability to think on your feet in a short amount of time. That's all it measures. That's why it's, when you take the science part of the ACT, they come up with these most random little facts, right? Because they want to make sure that you've never heard of that before. The whole purpose of the test is to see if you can take information that you have zero pre-knowledge about and figure something out about it. That's the whole purpose. I don't know much about it. But the ACT serves that sole purpose. An AP exam does that by, and also measures your knowledge of the subject. But it's still primarily looking for that rational, logical problem solving ability. And can you do it in a hurry?
Can we come back to this question for a while? Okay, so,
You gotta take a piece at a time.
well, I can do it again, drop my one.
Uh-huh.
I know H2O2.
Uh-huh.
And I know the 2-to-1 ratio there.
Right. So you're making half a mole of oxygen.
Yeah. So once you make that half a mole, what is it like? What is it like to like go for there?
All right. So that half a mole was collected in a 10-liter flask, right? Okay. So then they give you this little piece of information. Had you collected 1 mole in a 1-liter flask, the pressure would have been 24 atmospheres. So from that, you're expected to figure out what a half a mole in 10 liters would be. Okay. So you got a half a mole in 10 liters. All right. Had you had a 1 mole in 1 liter, the pressure would be 24. So a half a mole is half of 1, right? Okay. So you've got half the amount, but 10 times the volume, correct? So you're going to divide by 2 and multiply by 10. Because you got half the amount, 10 times the volume. No, I'm sorry. What did I say? Multiply by, divide by 2 and divide. What did I say? Multiply? Sorry. Divide by 2 and divide by 10. Sorry.
So does the 1 mole still say the same as just the liters section?
The question is about pressure.
I know, when you said the volume.
You're dividing by 2 because you have a half instead of 1. So you got to divide by 2. You take 24 and divide it by 2. Because you got a half a mole instead of 1. And then you got to divide that by that answer by 10 because you're in 10 liters instead of 1. So you divide it by 10. Divide 24 by 2 to get 12, and divide 12 by 10 to get 1.2. How do you get from 1 to 0.5? Right, by 2, right? Okay. How do you get from 10 to 1? Divide by 10, right? It's proportional stuff, right? If you look at those gas laws, Charles and Boyle and all those guys, it's proportions. All right. That better? I need to go home and ponder that one a little bit. Number 10. Oh, same question, same setup, different question. Which of the following identifies the element being oxidized and reduced? Oh, good question. This is a tricky question. Figure this out. You just go through and label stuff. Okay? So just go label the oxidation states. See it's going up, it's going down, right? Yep. Let's change it into the later unit. Now here's the tricky part of this that you got to remember something. What is the normally the oxidation state of oxygen in compound? Normally -2. There are 2 exceptions to that. One is if it's bonded to fluorine. Any fluorine in this system? No. The other exception is if it's bonded to itself, which happens in peroxide compounds, right? So what is the oxygen in hydrogen peroxide? What is its state? +2 is if it's bonded to fluorine. Okay. -1 if it's bonded to itself. So what's the hydrogen right here? +1. Okay. 2 + 1 is 2 - 1 to make 0, right? Okay. Right. What's the hydrogen in water? What's the oxygen? -2. What's the oxygen in pure oxygen? 0.
Oh, yeah.
Pure substance, right? Okay, so who's going up? H2O is not an element. H2O is a compound. Compounds don't have oxidation states. Hydrogen goes up, it's +1 and then +1. Who's just going up? Who is increasing? We wrote numbers on top of every element up there, right? No, hydrogen is +1, and then it's still +1. Oxygen went from -1 to what? 0. Which one went down? Oxygen. Hydrogen didn't change. Hydrogen didn't change. Oxygen went up and down. Okay. Hydrogen is the same, +1 and +1 on both sides, right? Didn't change. Okay. Oxygen is -1 on the left, on the right, it's -2 and 0. So some of the oxygens got oxidized and some of the oxygen atoms got reduced. So the question is, which of the following identifies the element or elements being oxidized and reduced in the reaction? One of the choices is oxygen. Both of them. Let's see. It's oxidized and reduced. Oxidized when it increases, reduces when it goes down.
I'm just making sure.
Oxygen is both oxidized and reduced, part C. All right, we got a word for that. Here we go. And the same thing as being both oxidized and reduced. There's a wrong word for that.
What?
Disproportionation. Disproportionation reaction is when the same element is both oxidized and reduced. It might. Maybe so. Okay. All right, everybody good with that now? We're not good with that? So you have to label the oxidation states, right? So you're labeling oxidation states of elements. The compound does not have an oxidation state. The elements within the compound have oxidation states. Okay? Compounds can have charges, but they don't have oxidation states. So you take a compound and you label the oxidation state of each element within each compound, and then look at it and see who goes up and who goes down. If nobody goes up or down, then it's not a redox reaction, right? It's just an exchange of ions. It's a double displacement. Maybe a synthesis or decomposition. It's probably a double displacement. If you find one going up, if one is going up, there has to be one going down, right? Everybody get that? Or vice versa. If you see one decrease, there's got to be one increasing. If you have one without the other, you messed up somewhere. One without the other is not possible. But you can have a situation where the same element is going up and down. And that's called a disproportionation. The elements potassium and chlorine react directly to form the compound KCl according to the equation above. We should be able to write that balanced equation also. It would be a good exercise for you to do at home. Is anytime you see that they're giving you a balanced chemical equation, you should start from scratch and see if you could write that. They're going to give you a lot of them, but they don't have to. And all of this would be good practice. Practice with writing them from scratch. Okay, refer to the information above the table below to answer the questions that follow. What remains in the reaction vessel after equal masses of potassium and chlorine have reacted until either one or both of the reactions have been completely consumed? Yes. So, in other words, reduce the excess reactant, because you know there's going to be product formed, right? So the other one would be there if there was an excess reactant. If you mix a stoichiometric equivalent, would you have any reactant left over?
No.
No. So stoichiometric equivalent is when you mix them at their mole ratio. Okay, that is not normally done. Normally there is an excess and a limiting reactant. If there is an excess and limiting reactant, then when it's finished, you'll have products and the excess reactant. So we got to figure out who the excess reactant is here. If we have equal masses of potassium and chlorine, okay, who are you going to have the most moles of? What's the molar mass of potassium? 39? 39 is close enough. You do a multiple choice question, so don't worry about the decimal. 39. All right. Chlorine is going to be 7. Okay. 235s, right? That's going to be 7. Okay. If I use 39 grams of each, just pick a number that's easy to work with in this situation. It's that equal masses, right? So if I pick 39 grams of each one, I got a mole of potassium, right? And a little more than a half a mole of chlorine. Can I follow that? Okay. Well, they react 1 to a half, correct? So there'd be chlorine left over. So the answer is KCl and chlorine. Where was the product? Have to have products.
Wait, I'm not gonna
Yeah, that's all zero.
Wait, I want you all. So why would it be KCl again?
It's a product. You have to form products. You don't have a chemical reaction.
So it says what remains in the reaction after the reaction, then it has to be the product.
KCl is definitely the product. So even if you don't have any reactants left over, you have to form products. So nothing, that means nothing.
Okay.
Okay. So the product has to be in the container somewhere. All right. The question is, is there anything else in the container, right? If you mixed a stoichiometric equivalent, the answer would be A, correct? Right? All right, let's follow along here a second. If you mix a stoichiometric equivalent, the answer would be A. What would the situation be from late last year's second semester? What situation would make D the right answer? Does this reaction have three products? You don't know, they got the balanced equation on your screen. What would make it D? What scenario would make D the right answer? No, that would make A. What'd you say? If nothing goes to zero, what do we call that situation? Nope, not bad. No, not doing third grade division. All right. What did we do last year when we did chemical reactions that nobody went to zero? Do I?
We thought about it a little harder.
Well, that's one thing you could call it, but that's not the word we're looking for.
Disproportionate.
No.
What does it start with?
Starts with an E. Equilibrium.
Oh, actually got it.
Equilibrium. Equilibrium. Okay. So if a reaction reaches equilibrium before it goes to completion, right? So going to completion, notice it says right here, reactants have been completely consumed, right? So that means you're going to completion. That means one or both reactants go to zero, right? Follow that? We got to know what that means, okay? When we get to the AP exam, it's going to be both types of things going on the same test, okay? So if it says completely consumed, that means somebody, at least one of the reactants has to go to zero. If only one goes to zero, that's the limiting reactant, and the other one is what? Excess. If they both go to zero, that means they were mixed as a stoichiometric equivalence. If neither goes to zero, that means the reaction reached an equilibrium balance before anybody got to zero, which is extremely common. Not the case here, but very common. Okay.
You know, it's so hard to follow along with you sometimes during this because like when you put the PowerPoints on there, like we're definitely not at like what we're talking about.
That's what we're talking about. That's a net ionic equation written on the board right there.
Yes, exactly. I'm trying to say like you're giving us a timeline, but like it's hard to follow that. We're trying to follow it day by day, and like you're on scope whatever stuff, like that's not even like 5
We covered all this last year. Oh yeah, every bit of this we could have answered this question last year. I'm not mad at you. Well, only when you ask something I either just answered or everybody knows the answer to it, including you. And I know you're asking it just to be asking it. Sometimes they do. All right, so there's the end of it. All right, left off on number 11. It's all about